Okay, so do you have any questions? No or many? Okay, so today we will be spending some time to study some ideal Bose systems. What I intend to discuss is the solids, or let's say the sound in solids, then blackbody radiation, and Bose-Einstein condensation, if time remains. Now let's start with the sound. Now if you take a solid, for example, so a solid is basically formed by just atoms fixed at their relative positions are fixed, but they are still allowed to vibrate. So if you try to write the Hamiltonian for the atoms, or the nuclei, if you like, for the metals, because the electrons will be free to move, but still the remaining semi-ionized atoms are still fixed at their position. So we have their kinetic energy plus some potential energy which depends on the positions of our atoms. Now, most of the time, the atoms will be just moving around their equilibrium position. So if we say that the Ri, let's denote by this, the average, this is the equilibrium position. Then we can just expand the potential around this equilibrium position. Or let's just call it Ri0. The potential at Ri0 plus the derivative of the potential with respect to xi times xi minus xi0 plus the derivative of the potential with respect to xi and xj multiplied with xi minus xi0, xj minus xj0 times 1 over 2 factorial plus all the remaining terms. Well, all these derivatives are evaluated at xi is equal to xi0. Now, what do we know? The xi0 is an equilibrium point. So if you would just imagine the shape of the potential, it doesn't depend only on the ith particle. This is actually, the potential depends on the coordinates of all the molecules. And here the derivatives with respect to xi is not the derivative with respect to the ith coordinate of some atom, but I'm just summing over all the derivatives of the potential with respect to all the coordinates of all the atoms. And so if you just look at how the potential changes as a function of the position of one of the atoms, let's say, it will have such a shape. And this shape, this is the equilibrium point. So what do we know about this equilibrium point is that the derivative of v at the equilibrium point it is 0. This is how we define the equilibrium point. Furthermore, the second derivative, let's take the determinant. This is larger than 0. So the first condition just tells us that it's an extremum. The second condition tells us that it is a minimum. So then the potential can be written as some V0 the potential energy in their equilibrium positions, plus, well, the first term over here, this is 0. It's just the second term. And for the second term, let's just call the coefficients 1 over 2 omega ij, let's say xi, xj. Now this omega ij, this is just the second derivative of the potential with respect to the ith coordinate and the jth coordinate. Now in this notation, I'm just saying, at the moment, I'm just assuming that V has 3 n coordinates. So this is the derivative with respect to the ith and the jth coordinate. I and j can go from 1 to 3n. Of course, this derivative is evaluated at xi is equal to xi0 for all. Xk is equal to xk0, let's say. And xi is nothing but xi minus xi0. That is the deviation. Of course, there are all the other terms which we will just ignore at low enough temperatures. Now then the Hamiltonian of the system just becomes pi squared. Well, this time this momentum is with respect to the xi coordinates. I can just make since xi depends on x by just a shift, the momentum relative to xi is the same as the momentum relative to xi. Divided by 2mi plus this, the sum over I and j, 1 over 2 omega ij, xi I, xij. This is my Hamiltonian. Now, of course, I can now make a change of variables and diagonalize this Hamiltonian, etc. So by a suitable change of variable, let's say eta I is equal to uij, xij, then the Hamiltonian just takes the form 1 over 2 p eta I squared, the momentum corresponding to eta I, plus 1 over 2 omega, let's say omega I, eta I squared. Well, this is nothing but a harmonic oscillator. So our solid, the vibrations of the atoms, or the cores of the atoms, we can just describe as, at low enough temperatures at least, in terms of just a sum of non-interacting harmonic oscillators. Now, of course, by adding the terms that we have ignored over here, these terms, we can also take into account the interactions of these atoms. But at low temperatures, they will not be important. And since they are just harmonic oscillators, we can determine what their energies are. The energy of a given microstate would be just sum over Ni omega I over all the modes. Or, let me just. H bar omega I and I plus 1/2. Or if we ignore the 0 point energy, this is just sum over I, H bar omega I and I. So we know the microstates, we know the energies, we can just write down the partition function if you like. So let's say the Q for n oscillators, now Q for the system, let's say, would be just sum over all sets Ni. Every set Ni just gives me a partition function, gives me a new microstate. And since these oscillators, they are, I can identify them. I can distinguish all these oscillators, so they are not indistinguishable oscillators. So it will be just sum over all Ni, h power minus beta, sum over I, h bar omega I, Ni. Or this will be sum over n0 from 0 to infinity of h power minus beta, h bar omega 0 to the power n0 times n1 from 0 to infinity e to the power minus beta h bar omega 1 to the power n1, etc. up to some n, let's call capital M, from 0 to infinity, e to the power minus beta h bar omega m to the power m, since I have a finite number of modes. Well, actually this m is nothing but 3n minus 6 for a general solid, let's say, because there are 3n degrees of freedom. 3 of them corresponds to translations, 3 of them to rotations as a whole. They are not vibrations of the atoms. So the remaining 3n minus 6 of them are just the rotations. So then Q just becomes product of I from 1 to, well, n is a huge number, so let's just say 3n. Of each one of those terms is 1 over e to the power minus beta h bar 1 minus e to the power minus beta h bar omega I. Or the free energy is sum over I logarithm of minus the logarithm of 1 minus e to the power minus beta h bar omega I. Now this is one way of looking at the problem. Well, an alternative derivation is, if you look at this energy expression, well, there are actually 3n minus 6 modes of oscillation, and in each one of these modes we have Ni energy packages. But these energy packages, we can identify them as particles. These are called the phonons. So in this sense, and these phonons are not interacting with each other. So in this sense, I can just treat this sound field as a gas of non-interacting phonons. Then I can ask, what is the average number of phonons in the ith mode? Well, the average number of phonons in the ith mode will be just 1 over, since they are bosons, e to the power beta h bar omega, or let's say beta epsilon I minus mu minus 1. But the number of phonons is not fixed. So you see this chemical potential, if you remember, we had to include that chemical potential to impose a condition on the number of particles we have. But now for the system of phonons, the terms we have actually ignored over here, these additional terms, they just cause the phonons to be created or destroyed. The number is not fixed. Since they are not fixed, we don't really need to impose this additional constraint. But that mainly means that mu is equal to 0. So Ni is just 1 over e to the power beta epsilon minus 1, epsilon I. Then the total energy will be just epsilon I times the number of phonons having that energy, summed over all the modes. So this will be equal to sum over all the modes, epsilon I over h bar omega I over e to the power beta h bar omega I minus 1. And the Q potential is just minus some of the logarithm of, well, what's the Q potential? For a system of bosons? Well, if you don't remember, you can just drive them. You see, I can just take my system as one of these modes, and if I treat one of these modes as my system, then the grand partition function would be just sum over the microstate of my single mode is given by the number of phonons in that mode only. E to power minus beta epsilon I minus mu times n 0. Mu is 0, so this is just 1 over 1 minus e to power minus beta epsilon I for a single mode. The Q potential for a single mode was defined as the logarithm of this grand partition function minus the logarithm of 1 minus e to power minus beta epsilon I, or the Q potential for the whole system is just minus the logarithm of 1 minus e to power minus beta epsilon I. Well, basically it's the same thing as the Helmholtz free energy. Basically, we are dealing with the same system. Now, of course, without knowing how to sum over the different modes, we cannot really proceed much from this point on. So, to calculate this sum, there are basically two different models we have, two very simple models. One is the Einstein model. Now, in the Einstein model, you see, what we need to know to sum over these i's is we need to know what these omega i's are. So what are they? Well, what will be the easiest assumption about the different omega i's? The easiest thing you can think of? The stupidly easy assumption. No, they have units. So there cannot be one, but one is a constant, right? So basically we can just assume that all of them are some constant. Let's call this omega e. It's just a constant. This would be the easiest assumption we can make. Then the Q potential will be just minus logarithm of 1 minus e to power minus theta e over t, or the A potential, whichever one you like. Let's say the A. Times, how many modes do we have? There's still sum over I of 1. What is that sum? What is R? What is I? How many terms do we have in this sum? 3 and minus 6. 6 is negligible compared to 3n, so that sum is just 3n. Now we know the Helmholtz free energy or the Q potential, whichever one you like, of the system. So let's see, what is the entropy of the system? Eventually we can look for what is the energy of the system. What is the entropy? It's just minus the derivative with respect to temperature at constant n. Well, this is plus 3 logarithm of 1 minus e to power minus theta e over t. No, sorry, here a is kt times this one. And sorry, a is with a minus sign. You see, a was minus the kt times the logarithm of canonical partition function. Q potential was just the logarithm of the grand canonical partition function. So this is plus kt. Let me also correct it over here. So when we take the derivative with respect to t, we get 3nk times the logarithm plus or minus 3nkt times the logarithm of the derivative of the logarithm, which is okay. There is a minus sign over here. When I take the derivative with respect to t, this minus cancels that one, but I still get a minus theta e over t squared times e to power minus theta e over t divided by 1 minus e to power minus theta e over t. So S is equal to, the first term is minus a over t plus, okay, this t cancels one of this one, 3nk Einstein temperature over t, 1 over e to power theta e over t minus 1. Energy of my system is just A plus Ts. But this is just 3nk theta e over e to power theta e over t minus 1. Or 3n, remember theta e, we had defined it as h bar omega e over k. So this is h bar omega e times 1 over e to power theta e over t minus 1. Well, this kind of makes sense because we have, let's say, this much particles in each one of the modes, and every mode has this on the average. Every mode has this much energy. So we have this much energy in every one of the modes, and we have 3n modes. So that's actually what we had obtained. Now we can look at the various limits, like the large temperature limit. Now in this case, the large temperature limit would correspond to just T much larger than this Einstein temperature, or theta E over T much smaller than 1. Now in such a case, 1 over e to power theta E over T minus 1 is approximately 1 over 1 plus theta E over T minus 1. This cancels, so we have T over theta E. So the energy of the system is just 3n. If you just look at this expression, h bar omega E T divided by theta E is h bar omega E over K. these cancels, so we have 3n kt. Now this is what we expect. So let's say every oscillation mode has 2 quadratic terms. So in total we have 6n quadratic terms. And in the classical limit, every quadratic term contributes kt over 2 times 6n. This is the average energy of my system. So the specific heat would be just 3n k. Now the other extreme, the small t limit. Again, small t just means t is much less than the Einstein temperature, or theta E over t is much larger than 1. Now if you look at the average energy expression, this is much larger than 1, so just we can ignore 1. So energy is just 3n h bar omega e h power minus theta e over t. Specific heat, which is just dE over dt at constant volume and number of particles, this just gives me 3n h bar omega e theta e over t squared h power minus theta e over t, and which basically goes to 0 exponentially at small t. So a specific heat basically has such a shape, as we have quite often seen in various quantum mechanical systems. At large temperature limit, it goes to the classical limit, which is given by the equipartition theorem. At small t, it should go to 0. Now, of course, this is a very crude approximation. You see, we had, if you go back, we are considering such a sum over I, and we just assume that all omega i's are constants. We can just improve it a bit. In what is called the Debye model. Well, this will be more precise at the low temperature limit. The basic idea of this Debye model is, especially if you go to the low temperature, you are not exciting the higher energy modes. So the higher energy modes will all be in the ground state. The main contribution to your sum will be the low energy modes. Well, low energy modes means smaller frequency, but small frequency also means larger wavelength. So if you go to the low temperature limit, the modes that will be important are the large wavelength modes, which these large wavelength modes cannot see the discrete nature of your system. So these are the so-called acoustic modes. The other high frequency modes are called the optic modes. So if we are looking at only the acoustic modes at the low temperature limit, so I can treat my system as a continuous system. So the frequencies will also be continuous. So I can just replace that sum by the dp, dq, dqp, dqq divided by h bar, logarithm of 1 minus e to power minus beta h bar omega I. Replace it by an integral. or let's say, just forget this h, it's just k. Well, the d cubed q integral will just give me some volume. D cubed k integral, I can just write it as 4 pi from the angular integrals dk k squared times the logarithm of 1 minus e to power minus beta h bar omega. Now, how is k related to omega? How is k related to the wavelength? How is it related to omega? Well, you can just look at the dimensions. K has the units 1 over mass, 1 over the length. And if you want to relate it to omega, which has the units 1 over time, you have to divide it with some constant that has the units 1 over time in it, mass over time. So that's the c. C being the speed of sound. Well, there's one thing we have missed over here up to this point. When you consider the sound waves, and if you look at their polarization, they can be transversally polarized or longitudinally polarized. Now, in general, they will have different speeds. So let's see here. It's not just the omega or the k values that determines a sound wave, but there's also the polarization. I didn't sum over the polarizations yet. So basically here I also have a sum over the polarizations. Of this expression. Now there are 3 polarizations. So let's say dk is just dw, k squared is just w squared. And for transversal polarizations, I have to divide by transversal polarization cube. There are 2 of them. And for longitudinal polarization, I have to divide by the speed of the longitudinal polarization cube, but there is just 1 of them. So let me just call this coefficient 3 over c squared, c cubed. C just in this final expression is kind of an average speed. Weighted average. So A becomes KTV times 4 pi times 3 over c cubed dw w squared times 1 minus e to power minus beta h bar omega. Well, we will manipulate this a bit further, but before going on, there is one problem. What is the value of omega? You see, if you look at this integral, a priori you would think that omega should start from 0 up to infinity. But as omega becomes large, this term becomes negligible. Here I have a logarithm. Okay. Well, you can think that omega goes to infinity, but you see omega goes to infinity means that you have a higher and higher frequency modes contributing to your system. But that is kind of contradicting our initial assumption. that we should have a finite number of modes. Well, to fix, so what we do is we just limit the omega integration from 0 to some upper limit, which is called the Debye frequency. Now, how do we determine the Debye frequency? Well, the total number of modes, this should be equal to 3n. Well, if you just repeat the same thing, this sum over 1 would be just v times 4 pi times 3 over c cubed times from 0 to omega d dw times omega squared. You see this kt term and this logarithm term is what was already inside the summation. So if I just remove them, I just get the summation without anything, just summing over 1. So I just copy this expression over here. So 3n is equal to 3 times 4 pi over c cubed v omega Debye cubed over 3. So let's just do the simplifications. Omega Debye cubed is equal to c cubed and over 4 pi b. Well, this is what Debye does. Well, one can actually improve this slightly by saying that, okay, the total number of modes is 3n, but there are 2n modes for the transversal polarization. So this should be equal to v times 4 pi 2 over c transversal cubed from 0 to omega Debye for the transversal modes. And for the transversal modes, we have this as c cubed n over 4 pi b. This is the Debye frequency for the transversal modes, and the Debye frequency for the longitudinal modes will satisfy a similar expression, cl cubed n over 4 pi v. But if you just convert them to some limits, let's say lambda Debye, whether it is transversal or longitudinal, this, if we define this as c transversal or longitudinal divided by omega Debye transversal or longitudinal, in both cases this is just 4 pi v over n to the 1/3. You see, v over n is more or less the volume of one molecule, or v over n is some typical number for the intermolecular distance. So this cutoff frequency basically corresponds to a cutoff in wavelength which is of the order of the atomic separation, which kind of is consistent because we started by assuming that the wavelengths that are relevant for us should be larger than the interatomic separation. So okay, so let's go back. We know what this omega Debye is, now it's given by this expression. Let me just define x to be h bar omega over kt, or omega is equal to kt over h bar x. So a just becomes kt times v, 4 pi 3 over c cubed. Well, I have omega cubed over here, which will bring kt over h bar cubed. Vx, x squared logarithm of 1 minus e to the power minus x, from 0 to some x0, where x0 is h bar omega Debye divided by kt. or the Debye temperature divided by the normal temperature. And we already know what omega Debye is, so we can determine what this Debye temperature is. So A becomes 4 pi 3 over c cubed kt to the 4 divided by h bar cubed times some function of x0. Now again, we can consider various limits like the small x limit or the large x limit. Small temperature or for the large temperature limit, you see x0, large temperature basically means the temperature is much larger than this Debye temperature. Or x0, theta Debye over t is much less than 1. So we are basically going to the x approximately 1 limit. Now, of course, we need some expansion of this dx0. For small x0, this will be d0 plus derivative of dx with respect to x evaluated at x is equal to 0 times x0 plus other terms. So let's look at what this function is for small x0. Well, d0 is, 0. D prime of x0 is actually x squared logarithm of 1 minus e to the power minus x. So d prime at 0 is this is 0. So the second derivative of d, okay, it is 2x the logarithm of 1 minus e to the power minus x plus x squared times e to the power, or 1 over e to the power x plus 1. So the second derivative at 0 is 0. Okay, the third derivative twice the logarithm of 1 minus e to the power minus x plus twice 2x of 1 over e to the power x plus 1 plus 2x, or another one of these factors, 4 plus x squared e to the power x over e to the power x plus 1. What is the third derivative? Really? You see, if you put x is equal to 0 here, this is just 1. So this is the logarithm of 0. So it's, let's say, not analytic at x is equal to 0. Now this is kind of not really a surprise. You see the second derivative has this logarithm. But you see we could have picked up from the logarithm. let's pick up this one. Now, if x0 is small, well, that means x is small. If x is small, this is equal to, from 0 to, let's say, x0 dx, x squared, logarithm of 1 minus x. Ones will cancel, so this is 0 to x0 dx, x squared logarithm of x, which is 0 to x0 dx, d by dx of x cubed over 3, logarithm of x. Now if I do an integration by part, this will be x0 cubed over 2 logarithm of x0, the lower limit will be 0, minus 0 to x0 dx, x cubed over 3 times 1 over x. This is 2. So d of x0 would be approximately, as x0 goes to 0, given by x0 cubed over 2 logarithm of x0 minus x0 cubed over 9. So this is one asymptotic, this is a small x0 expansion of d of x0. So let's go back. So this is our A. Now let's go on. What is the entropy? Entropy was minus the derivative of A with respect to x, with respect to t. Well, this is the derivative of t to the 4 term. That will bring up 4 A over t dx0. And then minus 4 pi 3 over c cubed h bar cubed kt to the 4. Derivative of the x0, but derivative of the x0 is just this one, x0 squared logarithm of 1 minus. Times the derivative of x0 with respect to t, which is minus theta d by t squared. Now, up to this point, I didn't make any expansion yet. Here I have a minus sign. Now, what we are looking for will be the energy of the system, which will be A plus Ts. No, sorry, there's no dx0 over there. So this will be minus 3a. You see, when I multiply this expression by t, there is a minus 4a over here. Then I'm adding another a. This is minus 3a plus 4 pi 3 over c cubed h bar cubed kt to the 4 x0 squared logarithm of 1 minus h power minus x0 theta d by over t. Okay, this is the energy. This is the energy we have.
Why don't we have, can you go up a little bit? Why don't we have dx0 at first term of s?
Here.
Huh?
You see, this is my expression for A. I'm taking the derivative of this with respect to temperature. Well, the temperature appears in this t to the 4 times dx0. First, I'm taking the derivative of t to the 4. It is this one. plus I'm just taking this one multiplied by derivative of the x0 with respect to t, which is derivative with respect to x0 first and then with respect to t. Okay. Now, did I make some mistake somewhere? Large t limit. Okay, so let me see, is this x0 correct? Yes. Okay. Because this is the energy of my system. Now x0, this theta d over t is my x0. So this is minus 3a. Cube times logarithm of 1 minus e to power minus theta d by over t. And then, well, you can just try to simplify it further using that theta d over t is much smaller than 1. So this will be approximately what you need to do is, let's say, take this, this is our A, this is the A, we know the expansion of dx0, put it over here, and there will be a logarithm over here also. What I expect is if you continue the derivation, there is a logarithmic term over here, which will cancel the logarithmic term over here. And at the end of the day, I will only have the contribution from this one. And the contribution from that one will just go to the classical limit. And we can also look at the other limit. This is essentially the easier limit. T much less than theta d. So theta d over t, which was x0, is much, much larger than 1. So if you go to our expression for d of x0, this is d of x0. x0 is much, much larger than 1. So the first thing that would come to my mind is, can we replace x0 by infinity? If we replace x0 by infinity, the contribution from large x values will be, you see, this is we cannot really replace x0 by infinity because, okay, the logarithm goes to 0, but I have this x squared term. So this integrand basically diverges in the large x0 limit. But let's see, we can maybe do some trick. If we do an integration by part from 0 to x0 dx cubed by dx times 1/3 logarithm of 1 minus e to power minus x. So this is 1/3 x0 cubed logarithm of 1 minus e to power minus x0 minus from 0 to x0 dx x cubed over 3. The derivative of this one would just give me 1/e to power x minus 1. You see now, this is for large x0. This is 1/3 x0 cubed logarithm of 1 minus e to power minus x0 minus from 0 to, now if you look at this integrand over here, for large values of x, it just goes to 0 exponentially. So in the second integrand, I can just replace x0 by infinity. Well, now x0 is becoming very large, so this number is very small, so this is dx0. For x0 much larger than 1, this is basically 1/3 x0 cubed e to power minus x0. This is the first term. Well, plus some constant. Let me just call that c. Now I can go back to A. In the small temperature limit, this is 4 pi 3/c cubed h bar cubed kt to the 4 1/3 theta d pi over t cubed e to power minus theta d pi over t plus this constant c. If I want to find the energy of the system, let's start with the entropy. This is minus dA by dt. Okay, you can just basically repeat the same treatment. And you see that, well, in this small temperature limit, both of this term and this term, they are both proportional to the positive powers of t. The first term also even has an exponential term, which goes to 0 at t goes to 0. And you can calculate the entropy, the specific heat, and you will see that this goes to 0. Kind of that's, okay, the specific heat should go to 0 because of the third law of thermodynamics anyway. Okay, any questions? Okay, let's give a 10-minute break now. Then we will do the black body radiation. Just 5 minutes.